Hi everyone. So today we're going to talk about circular motion, and this is not going to be a very long video, and in my opinion this is not something that is really hard to understand, but unfortunately my students tend to disagree, so hopefully this time I will manage to get the concept across. So the idea is that we're trying to analyze movement as something that's going around in a circle like this. And in order to do this, we find that it's much easier if we concentrate on the angle that it's describing than if we concentrate on the x and y position. Because if I concentrate in the x position, this would be going to negative x, then to positive x, then to negative x, and to positive x. This would be like simple harmonic motion. And if I would have to also concentrate on the y position, which would also be describing simple harmonic motion. And simple harmonic motion is complicated because there's sines and cosines and all that stuff. So hopefully there's an easier way to consider this, and that's saying, well, this is at a constant distance r, so that never changes from the center, and then the angle is just changing. So if I just tell you the angle, and I tell you how far I am from the center, then I'm telling you all you need to know. And this is much easier to analyze than if we're using x and y components. Now, the first thing that we need to know is that we're not going to use degrees for the angle, we're going to use radians. And we've talked about radians before, but let me just give you some motivation for how they work. The idea is that 360 degrees, so if I go all around this thing, this is 360 degrees, this is equal to 2 pi radians. So, simple. So, for every 360 degrees, we have 2 pi radians. So for 180, we will have pi radians. So which means that this angle is 2 pi radians, this angle is pi radians, this one is pi half radians, this one is pi quarters, and so on. So this is just a conversion. It's a simple proportionality problem. And you can understand it this way if you find it easier. However, there's a very good reason why we use radians, and the reason is that this is actually a proportion. It's the proportion between the perimeter of the circle and its radius. So you know that the perimeter is 2 pi r. And the radius is r. So if I divide them, I get 2 pi. Aha. And this is interesting because then I'm like, okay, well, so what if I take an arc, so this, and it has a length L? What angle is it going to have? Well, in radians, the answer is really simple. I just take L, and I divide it by r, and that's the angle in radians. So the angle in radians is nothing but the proportion between the length of the arc and the radius. When the length of the arc is the whole circumference, we get 2 pi. When the length of the arc is half a circumference, we get pi. When the length of the arc is L, we get L over r. So radians are the natural angle unit because they really help us to relate the properties of the circumference to the angles that we're following, and also because this is a ratio. This has no units. So the radian is not a unit. It's a ratio between two things that have units of meters. So this has no units. So when we write radians, there really is no unit. So this is the natural unit of angle, and you will see that it will make things way easier when we start calculating stuff. Okay. So now we're in a position to define these two things, angular displacement and angular speed. And the idea is that I have a particle that starts off here. So here's my particle. At t equals 0, it's here. Okay, and then after a certain time, let's say t equals t, so I just call it the time t, then it's at a certain angle theta. Okay, so this guy has moved an angle theta. Well, the angle that this guy has moved, we call it the angular displacement. So that's it. Okay, so we say, okay, so this guy has moved an angle theta. And the angular speed is just how much angle this guy has moved per second. Okay, so if this guy took a time t to move an angle theta, how much angle per second did he move? Pause the video and tell me. Okay, hopefully you figured out, well, if it, let's say that it did 4 radians in 2 seconds, then that was 2 radians per second, so you just divide, right? So, oops. So, good. Okay. This thing we call the angular speed, and we write it with the letter omega. This is a Greek omega, this is not a W. It's like a weird W. Okay. So, now we just learned our first thing related to circular motion. This is the angular displacement measured in radians, remember, and the angular speed is just the angular displacement per unit time. So you can see that this works exactly the same way that the linear motion works, right? Here we would put the distance, here we would put the speed. Same thing, but with an angle and an angular speed. And of course, now that we have the angle and the angular speed, we can start speaking about the typical things that relate to circular motion. Actually, they also relate to oscillations, and that is frequency and period. Okay, so what do you think period could mean in the concept of circular motion? Pause the video and tell me. Cool. Well, hopefully you thought, well, the period has to be the time that it takes to go a full circumference, and you would be right. So let's think about how to calculate it. Well, a whole circumference is 2 pi radians, right? And my angular velocity tells me how many radians per second I do. So how long does it take me to do 2 pi radians? Well, easy. It will take me 2 pi divided by how fast I go. So the faster that I go, the shorter it will take me, right? And this is just the formula for period. And you don't need to know this because you can deduce this every single time, and also it's in your data booklet. Now, how about the frequency? Well, we know that the frequency is nothing but 1 over t, right? Just like in waves and oscillation and all that. Therefore, if frequency is 1 over t, then frequency has to be equal to the angular velocity divided by 2 pi. And that's the second formula that we need to know. But again, you can deduce this anytime, and it's also in your data booklet. Right, so now imagine that I have the angular speed of something, and I also have its angular displacement, but I would like to know the length that it's gone through, so this distance, or the arc of the circumference. So I would like to know this L, and I would also like to know its linear speed. So I would like to know V. How can I do this? Well, I'm going to start doing it with that, and then you'll see that it directly applies to this. Well, I know that the angle is nothing but this thing divided by the radius of the circumference, but because that's how we defined that. So we know that the angle is just L over R. So if I want the displacement, all I need to do is rearrange this equation, and then I get that L equals the angular displacement times R. So if I want to get the linear part, so the part where it's about meters and not about angles, all I need to do is I multiply by R and I'm done. But this only works if theta is in radians. If theta is in degrees, then you have to do a lot more. That's why we do things in radians, because it makes things way easier. Now let's think about, what about the angular velocity? Well, the angular velocity basically tells me how much angle per second, right? So again, if I want to get the actual velocity, I get how much angle per second, and remember that the angle is the length over the radius, so I just multiply by the radius and I get the length per second. So W R, well, it's not really W, it's an omega. So that's how I go from angular to linear. I multiply by R. What if I have the speed or the arc of the circumference and I want the angular speed and the angle? Well, I just divide by R. So I can just multiply by R and divide by R in order to go from angular to linear and vice versa. Couldn't be easier. Okay, and this is the last thing that we're going to do, and maybe the hardest to understand. So the first thing that I want you to ask yourself is, imagine that I have this thing that's moving in circular motion. Pause the video and ask me, is its velocity constant? Yes or no? Okay, hopefully you did this, and I certainly hope that your answer was no, its velocity is not constant. Why is it not constant? Well, because its velocity, remember, is in 2D. So you have a y velocity and you have an x velocity. And obviously, as this guy is changing direction, the x velocity is changing and the y velocity is changing. So this guy is not moving at a constant velocity. Its speed is always the same, but its velocity is always changing. And remember that if there is a change in velocity, then there is a force. So again, this is not moving in the absence of forces. You need to do a force in order to change something's velocity. And this thing's velocity is changing all the time. Now the next thing that we can ask ourselves is this force doing any work? Pause the video and tell me. Well, this question is a little harder, but it can be answered relatively easily. So if I have this guy here, then its speed is just going up. And if I want it to go this way, I need to do a force that goes towards the center. So I need to do a force this way, so that this angle here is 90 degrees. And what does that mean? Well, remember that the work is force times distance times the cosine of the angle. And in this case, the angle is 90. So the cosine of 90 is 0, therefore this force is not doing any work. What does this mean? Well, since it's not doing any work, then it's not going to alter the energy of this thing. It's not going to give it any kinetic energy. That's why the speed remains constant. But there is a force that is required to change the velocity of this thing. It's just that the force is always perpendicular to the movement of this thing. So the force is always pointing towards the center of the movement. So as this guy moves this way, the force always points towards the center, never does any work, but keeps changing the velocity of this thing. Now this force that's always pointing towards the center is called the centripetal force. Guess why? Because it points towards the center. And this should not be confused with the centrifugal force. In fact, the centrifugal force is something called a fictitious force because it's not real. When I am in a place somewhere that's rotating, I feel a force that takes me outside, but that's because I am not in an inertial reference frame, in the sense that the reference frame where I am, the place where I am, is not moving at a constant speed. So I feel these forces that don't really exist. This is not really a force. I'm just feeling the inertia that I really want to keep going this way, and my car, for example, is forcing me to go this way. So I feel pulled out, but I'm not really being pulled out. I'm being pulled in by the car. Okay. Of course, if there is a centripetal force, there has to be a centripetal acceleration, and the centripetal acceleration is the one that is changing this velocity here. And it turns out that we can calculate the centripetal acceleration, but doing so requires knowing differentials. So I'm going to kind of derive a formula for centripetal acceleration that's not going to be very rigorous. And then when you know differentials, then we can talk about this a little longer. Here's the idea. Now, I ask myself, how much acceleration do I need in order to keep this moving in a circle, right? And the acceleration is related to the force, right? The more force that I need to do, the more acceleration, and vice versa. So I'm like, well, okay, if I'm going really fast, it's going to be harder to keep me spinning in a circle, right? I'm going to have to pull more strongly towards the center. Therefore, the more speed that this thing has, the more centripetal acceleration that I should be feeling. However, if the radius is very big, then it's easier to keep me spinning, whereas if the radius is very small, it's harder to keep me spinning because I need to deviate each thing more each time. So this should be inversely proportional to the radius. Now let's see if this works. I'm going to check my units, as I did the other day. I need to get meters per second squared, and the speed has meters per second, and the radius has meters. See, I have a problem because meters and meters are going to cross out, and I'm going to have something divided by second. So I'm missing 1 meter and 1 second. But that's good, because if I'm missing 1 meter and 1 second, it's easy to add them. I just need to square the speed. If I square the speed, then I get meters per second here, and second squared here. Then only the squared goes, so this goes with that. And then what I get is meters per second squared, which is exactly what I need for an acceleration. So again, with this pretty crappy proof, this is the formula that gives me the centripetal acceleration if I have the velocity. What if instead of the velocity I have the angular velocity? Well, it's pretty easy to deduce, because we know that the velocity is the angular velocity times r. So in this case, the centripetal acceleration is going to be angular velocity times r squared divided by r, and that's the angular velocity squared times r. So if instead of the velocity I have the angular speed, then that's the formula that I use. How about the centripetal force? Well, force equals mass times acceleration, right? So the centripetal force is just the mass times the centripetal acceleration, which is the mass times v squared over r. And that's all we need to know. Again, for a more, proper derivation, let's wait until we know differentials. Now, as you can see, I didn't go through a lot of these things because these things are going to be in your problems. So, for example, identifying the forces providing the centripetal force, you're going to be doing a lot of problems involving this. So you need to think through what is the force that's pointing towards the center and figure things out. Of course, solving problems, you're going to be doing this, but at least I introduced you to all the relevant problems. So now you have the tools to solve the problems. And finally, qualitatively and quantitatively describe examples of circular motion. In this case, again, it's going to be up to you in the problems. So good luck. Remember, this is way easier than it looks, and if you have any problems, I'm here to help. Bye, guys.